Thank you very much for, for all the honors that the Italians have given me over the years. My very, very first honor was actually an Italian medal, Sacconi medal, that was given to me by the Inorganic Italian Society, and then the ENI, and then last year the Belsen Prize, which in the end was a precursor to the Nobel Prize. And today I'm quite honored to be a member of the Académie de Linci. The Nobel Committee cited the development of metal organic frameworks, and this is something I want to talk about, but I also want to talk about the future. I want to talk about the birth of this field, how it became what it is today, but then I want to move very quickly to what the future holds for this field. Let me begin by saying that civilization rely on how well we can design materials. In fact, we rely on materials so much that we name our ages after materials such as the Stone Age and the Brass Age and the Iron Age, the Cement Age, the Glass Age, the Silicon Age, and the Pharmaceutical Age. And the nice thing about this is that as we learned how to design matter on a finer and finer level, so did the benefit for society grew, and so did the economies became larger and larger. And of course, the ultimate design on the atomic molecular level is really the design of metal organic frameworks. So I was very, very happy that in some of the Q&A, after the announcement of the Nobel, that a member of the Nobel Committee said, many say that we live in the age of MOFs. I was very pleased about that because, of course, I believe that we live in the age of MOFs. I believe this is the 21st century of MOFs. In the beginning, metal organics complexes were made by Alfred Werner, and if you look at their crystal structures, they incorporate small molecules such as benzene inside the interstitial benzene. It's almost like a guest in a pore. And later, in the 1960s, Richard Barrer, who is the inventor of the templating effect in zeolites, did look at this compound and showed that it takes up gases. But in fact, it only can do one cycle of uptake of a gas and release. And because it's molecular, the complexes are only held together by weak bonds, the material collapsed on itself. So it did not sustain porosity. And of course, we're all familiar with Prussian blue. These metal cyanides, they are truly porous. They remain open in the absence of guests, and they have many uses. And also, the layered analogs of Prussian blues, these famously nickel cyanides, where you have interstitial benzene units that are enclathrated between the layers. I don't consider these metal organics because a cyanide unit is an inorganic unit. We can't functionalize it. So unlike a MOF, where you have an organic unit that is where you can functionalize and do reactions on the linker, the cyanide is just an inorganic unit. You can't do any reactions on the cyanide linkage. So they're different than what we'll be talking about. Okay. All right, so the early coordination networks, believe it or not, metal organics such as the one I'm showing here, it's a copper 1 linked by adiponitrile to make a diamond framework, an open framework. This was reported back in 1959. And in fact, more of such structures were reported later, such as in 1986 by this German group. Same compound, same kind of linker, and again copper 1. In 1989, Robson made this, again, copper one with the same diamond-like structure to make a diamond framework with the BF4- units, ions filling the pores. They're all very similar, except Robson foresaw that you can expand the linkers and make progressively larger and larger pores. And he showed several examples like that. At the time, there were many others who were involved in this, such as Fujita in 1994, Zawaradko, and in all cases, including Robson's, the linker was always neutral, not charged. And so even my own group, back in 1995, the student came in and started putting these together. In fact, at the time, I said to the students, please stop working on these because they're not very useful. Okay, there's many of them, and taking neutral linkers such as bipyridine, linking it up with copper one, well, that's the same as what's been done before, very similar to what was done before. But we, as advisors, have an obligation to sit down with students and publish their work. And so as we were sitting down to publish this work, I realized that there is an opportunity here because these structures were beautiful but frail. They collapsed when you try to use their porosity. So in many ways, they were sculptures and they wouldn't be useful unless you could show beyond doubt that they remain open in the absence of guests inside the pores, that they have architectural robustness. And that's what we set out to do. And I have this portrait in my conference room, staring down at every student that goes into that conference room. And I sometimes ask the students, what do you think she's telling you? Okay, look deep into her eyes and tell me what she's telling you. And of course, they always think that I'm silly for asking that. But I always thought that she's saying you can do better and you can do more. And that has always been our motto in the group. I admire Marie Curie because of her personal history, but also I think that she was a determined scientist. So she's always been a great, inspiring example. I wrote an article in this journal about this portrait and what it means in terms of mentoring students. So the question that we wanted to ask to do better and do more is what happens when molecules interact strongly? Instead of a bipyridine, or instead of neutral linkers that interact with metal ions, that bond is worth about less than 100 kilojoules per mole. But if I could put a charged linker instead of a neutral linker with transition metal ions, then such as carboxylates, then that bonding interaction is much stronger because now you have a charge-to-charge interaction. And so that bonding interaction would be 3 times as strong as the traditional networks. And that same student that I was talking about before, she tried this reaction and then she got a powder diffraction like this. And all of you know that when our students do X-ray diffraction, they get something like this. They run a mile away. They don't want to do this project because it's impossible. Okay, so it means that they made some, we used to call it junk, and with poorly crystalline and ill-defined material. So she set out to address the crystallization problem, and I think for this audience, probably I don't need to go through this in detail, but the crystallization problem has 2 components. It has a thermodynamic component where you need reversibility in linking building units together so that they can attach and detach and make sure that they come together in an ordered way. And you need to pay attention to the kinetics, because if it's too slow, the assembly is too slow, then you never get to the big crystal that you can characterize. If it's too fast, then they don't have time to be reversible, and therefore they make amorphous stuff. So that's what we were able to do. And in plain words, we were successful in identifying the conditions, the recipe, to balance the thermodynamics and kinetics and make crystals of what otherwise would have given you a very broad X-ray diffraction. And this was it. This was the very first. Compound we made from a trimesic acid that is negatively charged with cobalt 2+. And this is the first example of a crystallized metal organic framework. We call them metal organic frameworks because they're made from metal, they're made from organic linkers, and they were frameworks. And that name stuck. As you'll see later, I collaborated with German scientists in BASF, and they were calling them MOFs. And so it became very, very common. Guanming Li was the student that cracked the door open. She came to me when I was assistant professor, and I sort of wanted to push her away because my lab was not ready. And she kept insisting that she joins my lab. Finally, I took her in. 20 years later, she explained to me that the reason she was enthusiastic about joining my lab has nothing to do with me or my scientific objectives, was that no one was accepting her in the department. And she was selling flowers on the street in Phoenix at the time to make a little bit of money to survive. So it was actually a very touching story. But Guanming was the student that cracked the door open and showed us how we can crystallize these. Then Halian came in, and Halian was the student I met when I was an intern in China. And after I became professor at Arizona State, he wrote me a letter, which I still have, that basically said, congratulations on becoming a professor with a lab, doing what you're doing. I think I can do it better than you. And I said, well, if somebody can do my research better than me, hell, I should hire them. And so I brought him in, and he made this. He was really great. Halian will be one of the official invitees to the ceremony in Stockholm. I'm very proud of him and of what he has accomplished in my lab back when 30 years ago. So more than 30 years ago. So here, this is the recipe that basically allowed us to crystallize these systems, and this is a 2D layered structure where you have the paddle wheel. Every inorganic chemist knows about these paddle wheels. They're very common for zinc acetates and copper acetate, but now instead of a molecule, we linked it up with this ditopic linker to make a grid. And in this grid, you have pores with DMF molecules that are acting as guests. And the big question was, could you remove the DMF molecules, and will the structure remain open and therefore has permanent porosity? And the answer came. Well, before we get to the answer, as we were publishing this work, we saw this work by Kitagawa and Angivante Shami, where he had pressurized this material and showed that it can take up gases under pressure. And years later, I critiqued this work because I said that once you pressurize anything, it takes up gas. It doesn't have to have permanent porosity. Permanent porosity means that things must flow in and out of the pores spontaneously without having to pressurize them. And so it was Mohammed Adaudi who I met in Lyon very early on when I was supposed to give a talk that I missed because I overslept. They sent Mohammed to come and pick me up from the hotel. And he asked me for a postdoc. So I said, of course, you can come and do a postdoc. But he measured the first gas sorption isotherms and showed beyond any doubt that, in fact, these structures could remain open in the absence of guests. This was the absolute very first proof, beyond doubt, that these structures remain open and had architectural robustness. The reason I mention these students is that there's a lot of a lot of interactions with students, a lot of mentoring and discussion with students that makes a big difference in research. And these students were resilient. I mean, they could withstand a lot of pressure in carrying out their science, and so these three really helped open the field. Now, from the sorption measurements, you get a surface area, and so the surface area here was unexceptional to 175 meters square per gram. That was like an average zeolite at the time. So we were, people were not impressed with that. I was, because it was the very first time you show that a metal organic structure could be made porous, and it allowed us to compare these results with the more established materials such as zeolites and, in those days, mesoporous structures. These are the reviews on those papers because it shows you exactly what was going on during that time. It says this manuscript should be of wide appeal to a general audience interested in synthesis and use of metal organic framework porous materials. Invariably, the porosities are generated by removal of solvent and organic groups or by topotactic structural rearrangement. Until now, the major limitation of these materials has been in the ability to create systems with the necessary structural stability through low temperature assembly techniques. This work is a benchmark for solving this problem. Here's the second review, which says this work represents a significant advance and demonstrates for this first time the microporosity which can be induced in the open framework of metal organics. Third review, very similar. I agree with the authors when they state that the establishment of porosity in the open metal organic frameworks is important. This has been and continues to be a concern publications involving this class of materials. In that regard, I find this paper refreshing. The reason I'm taking you through the agony of reading these reviews is because it showed there was a departure from the old-fashioned neutral linker metal ion structures into this new arena of making materials with the strong bond and the proof of their microporosity. Well, we were really now very excited, and in 1999 we reported MOF5, which turned out to be an archetypical MOF, and we put the yellow ball there to indicate the space within which you could incorporate structures. And the reason these structures are just so touching, I would say, is that they're made from clusters, in this case a tetrazinc carboxylate clusters that have been around since Bragg. I mean, Bragg was the first to characterize these using single crystal X-ray diffraction. They were sitting there for almost 100 years before we came along and linked them up to make frameworks. And this is Mohammed again, showed that in fact these have extremely high porosity, 2,900 meters square per gram. Well, this got people's attention, not only the beauty of the structure, but also the fact that the surface area was at least 6 times more than the most porous structure previously reported. So this was really, really exciting. In fact, 1 gram of this material, which wouldn't be larger than a European sugar cube, encompasses as much space as an entire football field. Okay, think about that. So the interior is much larger than the exterior because it's filled with these microscopic pores. And this is a demonstration. This requires audio. In this demonstration, we'll show how an empty canister versus a canister that has a MOF, and the canister that has a MOF holds more gas than the canister without the MOF under the same temperature and pressure. Okay? Let me repeat. The empty canister versus the canister with the MOF. The canister with the MOF holds at least 3 times more gas than the one that does not have the MOF, because the MOF has those microscopic pores that compress the gas and allows the interior of each granule to be much larger than the exterior. And so this is what
this experiment provides a striking demonstration of MOF storage capacity. The pear-shaped glass container on the left is empty. The glass container on the right is filled with a MOF material. A vacuum is created in the container without the MOF. This container is then filled with the gas at 10 bars of pressure. The apparatus with the empty glass container is now weighed using Terz scales. Exactly the same procedure is repeated using the glass container with the MOF. The scales prove it. The MOF container has more than triple the amount of gas inside for the same amount of pressure. The gas...
Okay, this is why that happens, is that you have, when you zoom in on each granule, it's almost like bees on a honeycomb. Instead of gases filling very large volume, the attraction of the internal pores for that gas allows you to compress more gas per unit volume than you would without the MOF. So the MOF acts like a honeycomb for bees to assemble onto them. And here you can see gases being compressed inside the pores by virtue of the anterior of the pores being much more attractive to a gas than with the MOF than without the MOF. Okay, so it didn't take long after that to show that in fact, like in all chemistry, once you know how to design one thing, then you could extend it to designing others, but now with different functionalities and therefore different different crafting the interior with different functionalities, okay? Also, you can expand them by using progressively larger and larger linkers, okay? So that showed that you could design materials, you could design their interior chemically, you could design the pore size, and it was the very first time in chemistry where this is possible beyond the molecule, to be able to do this with extended structures. The Nobel Committee was very interested in this idea, and they called it rooms for chemistry. These porous structures, they think of them as rooms for chemistry where these rooms could be tailored for different molecules to reside inside the pores. And so at my first zeolite conference, or the first conference where I reported MOF5, there was a German scientist from BASF in the audience, and he caught me after my lecture and said that the number was so unbelievably high, that's a surface area number, I thought it had to be a misprint. And so then they were trying to reproduce our work. And fortunately, it was quite reproducible, and they were very impressed by these high surface area numbers and started a very nice and productive collaboration that lasted for 17 years. And during this, they showed that in fact MOFs could be made in multi-ton quantities, and they're not just laboratory curiosities. This was a very important development at the time. This is one of the MOFs. I think this is MOF5, shown here in this big blue buckets, and this is a plant that produces the MOFs. MOFs have now moved beyond the laboratory, and my colleague George Shimizu has made a MOF using very similar techniques to what I just explained, and which is being used now in cement plants to trap CO2 before it reaches the atmosphere. And BASF is making hundreds of tons of this MOF and supplying at least 3 plants in Canada that deploy this technology. And here, as of publication of this work back in, I think, 21, by 21, this material has cycled over 450,000 cycles. And that's because of the strong bonds that I've been talking about. That's because of the permanent porosity, that things don't collapse as you cycle gases in and out. They remain open. So this is a big commercial success. What about the future? Well, there's COFs. They were not cited by the Nobel Committee, but they exist, and they're growing even more rapidly than MOFs. We made them back in 2005 and 2007. They're all organic structures linked by covalent bonds. Carbon-carbon bonds, carbon-boron bonds, carbon-nitrogen bonds, some of the strongest bonds known in chemistry. And let's talk about one of these COFs, COF 999. COF 999 is made from a backbone here in blue and pink that is made entirely of carbon-carbon bonds, carbon-carbon double bonds and carbon-carbon single bonds to make a really robust structures. And then the interior is decorated with amines. You see them here. And here's an Italian connection. This is Laura Gagliotti, who's also a member of this academy, who's been helping us for many years to explain, using computation, what's happening inside the pores. So here's the experiment that really that is truly a fantastic development. We took open air in Berkeley and measured the CO2 concentration in the air outdoors. Then we took its measurement of the relative humidity in air. And this is over a 21-day period. And then we looked at how much the CO2 taken up by the material. So basically you take a powder of the material and then you expose it to air. And the air is coming from outside. And you pass it through the material and you look at what's happening on the other side of the material. Well, it takes up CO2 and there's absolutely no CO2 left in the air once it goes through. And you see that it takes up CO2 very nicely, and the CO2 uptake scales with the humidity. The more humidity is in the air, the better is the uptake. But if you take one humidity level, let's say 37%, it will look absolutely reproducible. So this variation is a variation that corresponds to the humidity rather than the stability of the material. This material can cycle. In this report, we cycled 100 times with absolutely no imprint left on the material. This is the kind of stability you need to have a viable material for CO2 capture from air. So this is the capacity is 1.5 millimole of CO2 per gram. When we publish this work in 2024, now we have 2 millimole of CO2 per gram, and it could be used not just for air, but also from flue gas in power plants that use natural gas and coal. So I like to say that the CO2 capture problem, the scientific problem, is solved. Yeah. This challenge is solved. This material can cycle and cycle for 6-7 years. Why? Because the chemistry of the backbone allows the backbone to be robust. So now we want to talk about what you need to make this scalable or to operate this at scale. In the air today, there's 1,100 gigatons of extra CO2 that we need to capture. This is the additional CO2 we put into the air as a result of burning fossil fuels. Okay, let's say I have COF 999. We just improved it to 2 millimole of CO2 per gram of COF. We can improve it more. We're only using around 20% of the amines. So potentially we might be able to double this, triple this. There's capacity for tripling this. And the cycling can be done very fast because the MOF framework, as I showed in the movie, is quite open. So the pores never get clogged. It's really a scaffolding, and things can diffuse in and out very quickly. So with these parameters, I need 100,000 tons of COF to capture half a gigaton of CO2 every year. Okay? So if I put that kind of plant in 700 or so cities around the world, cities that are 1 million or more, we could trap that CO2, remove it from the air in about 3 years or so, 3.5 years. Okay? But that means that every country that has 1 million or more have to deploy this technology, or at least the G20 would have to get together and say, this is not just a problem, but it's a crisis. We need to address it, and here is the science is already there. And that's what it requires. I don't think it's enough for Italy to do it, the US to do it. I think it needs a collective effort because of the amount of CO2 that is in the air. And don't be alarmed by these large numbers. 100,000 tons of cough, that's nothing to the chemical industry. They already make 200 million tons worldwide of sulfuric acid every year. So it's a scale that our chemical industry is used to working at. So I would say that this is should be our next frontier, is to convince our society where we live that this is a crisis, not just a problem. Just like the pandemic was a crisis and everybody united over solving the pandemic problem. Every time we had, in the US, the housing collapse, within 2 years we were back up on our feet. Why? Because we said that's a crisis. So we pumped tons of money into it and made it go away. In this case, it would be an investment, because if we try to capture the CO2, we invest in it, then you're going to see the CO2 conversion to something valuable become an economy on its own. This whole thing is going to generate a new economy. It's not just a liability for society, investment that you're not going to get a benefit from. Okay, so we remember this is a segment about what's next. So what's next is also weaving. I think this requires you to do it by hand. All right. Well, anyway, molecular weaving is basically threads of organics that are interlaced in and out of each other in a periodic fashion, and they impart extremely strong mechanical properties onto material without them becoming brittle. So that's still an area that is being developed. Finally, I want to talk about asymmetry. How much time do I have? Do I have 5 more minutes? 5 minutes, okay. Asymmetry is a new field that's emerging. I like to call it asymmetry because it's AI cross with materials, cross with chemistry. And I define it as a science of using AI for the design and synthesis of materials and for connecting chemical structures to properties and vice versa. We want to be able to, remember, we have millions and millions of possible structures. First, we want to figure out how to choose which structures are important for a particular application, but also if society comes in and says, let's take PFAS out of water, what structure should we use? We need to develop that as well. So structures to properties and then properties back to structures. I think that's the mode of operation for asymmetry. So how can asymmetry accelerate this chemistry? One is that we can accelerate the discovery of new frameworks. Okay, it takes, in my lab, it takes, excuse me, let me go back. In my lab, it's easy to make a moth or a cough, but it's much harder to crystallize these things. You need them sometimes, for many applications, you need them to be crystalline. So, for example, for water harvesting from air, you need the material to be crystalline so that it has efficiency when it's energy efficiency when you're removing the water. I'll explain that shortly. But second thing, so it takes long to crystallize. We need to speed that up. We need to be able to predict structures and link them to properties. That's still a big problem in science. Making a structure then have a predictable property. And then we need something for synthesis planning and experimental guidance, and to try to get away from human bias in doing that. Okay, so I'll show 2 examples here. Example number 1 is Zach looked at our water harvesting system and said, okay, I could use ChatGPT to molecularly edit the linkers so that we can optimize the water harvesting properties. This is a very nice water harvesting material. And we published this back in 2021 with Laura Gagliotti, but we also characterized not just the actual structure, but exactly where each water molecules goes into this structure has been characterized by single crystal X-ray diffraction. In fact, this was the occasion where I challenged Laura. I said to her, I don't believe in any of these computations unless you could predict where these water molecules will sit. And she certainly did. I was absolutely amazed. And in fact, we knew the answer from experiment. But I wanted to see how, I know it's really not very polite to do that, to challenge somebody when you know the answer. But I wanted to see how good computational chemistry has gotten. And it's an amazing field. In fact, after this occasion, I started shifting my group to do experiment and computation AI because of the power of these models that Laura and others are working on. So Laura got the location, or the exact location of the most important water molecules in the pore correctly. And that should make a believer out of all of us in computational chemistry. So here, I'm going to excise one pore out and slice it to show you exactly where each water molecule goes. It goes first to the hydrophilic sites. That's 4 waters go into the hydrophilic sites, and then as the hydrophilic sites get filled up, it bridges over the hydrophobic sites, thereby filling up the pores. So what I'm saying is that if you're a water molecule floating inside the pore, you're experiencing patches of hydrophilic and patches of hydrophobic. And this push-pull to water allows you to control how tightly water is bound inside the pore. That's why you could remove this water under ambient sunlight, just by heating under ambient sunlight. That is so important ultimately to commercializing this, because I don't need to necessarily bring in expensive power to remove the water. I could use waste heat, or I could use ambient sunlight. So these water molecules could be removed at 45 degrees or 50 degrees Celsius. So the students took this to the desert and showed that, in fact, you could make a device that is pancakes of MOF, and when exposed to air, it takes up water from air, and during the day, when it's hot, you put it under sunlight, and it generates water. Okay? Water is no energy input aside from ambient sunlight, and it's pure, ultra pure water. This is the most clean water you'll ever find, because the MOF is a filter in itself on the microscopic level, and the components of the MOF don't leach because of the strong bonds holding them together. Okay, so ChatGPT, we use it to fine-tune this. So we gave it some initial guesses, and it worked on generating different linkers of different composition and even mixed linkers. And we made the corresponding structures using robotics and tested them, and it turns out, I won't describe everything on this slide, but it turns out that those MOFs from ChatGPT turned out to be the very, very best water harvesting materials. Okay, so and that's because ChatGPT is not looking in a small spot. It's looking across the entire literature and taking that into account. And we as researchers don't have that capacity, especially not as fast as ChatGPT would be able to do it. So this is going into production, and here's a device that is powered. This is a powered device that will give you 2,000 liters a day, every day for the next 6-7 years. And another device that works entirely on low-grade heat or ambient sunlight, and this gives you 850 liters a day, every day, for the next 6-7 years without having to replace the MOF. Again, it goes back all the way to chemistry, the strong bonds and the ability to make materials that are architecturally robust. Okay, finally, I just want to share this with you. I won't describe the whole thing, but now we want to build a platform that I call molecule to society. I just showed you that chemistry can go from the molecule to the material to the device and to commercialization. Why not build an AI computing platform that facilitates this molecule to society? And you have initially what Laura does the design with generative AI, prediction of the structures, then making of the structure using robotics, and then scaling. Actually scaling it up and scaling across society and making commercializable products on this platform. And as you go through these cycles, the models get better and better and better. So the vision is, can we make materials better, cheaper, faster, and greener using AI? And I just want to tell you that at least these two cycles already are working very well. And I'll finish with this. For example, in this data set that we did on robotics, we generated 2,688 data points. And from that, we modified the machine learning algorithm to make it more adaptive and more chemistry intelligent. And it turns out that when you use that machine learning algorithm, you discover more materials, double the number of materials than if you didn't. Okay, and some of them are ordinary, meaning that if I look at them and say, well, I could have guessed that. And some of them are extraordinary and unexpected. So AI or Ametry is transforming the way we do chemistry in my lab. And I think that we're going through a revolution in taking chemistry to the next frontier, which is a frontier where we're using computation AI and deploying it as fast as society is, and that chemistry should not be moving on geologic timescales, should be commensurate with how fast society is using it. I mean, AI and computation have transformed banking and commerce and transportation, aviation. I don't see why it wouldn't transform science, and specifically chemistry. So I think the future is very bright, and the Nobel Prize citing development of MOFs is only the beginning. There's a lot more to be done, a lot more fantastic developments that will have a bear on solving societal problems. So finally, I want to thank my wonderful group members, the people who have funded my research, and thank you for your attention. It's an honor to be inducted in this prestigious academy. Thank you very much.
Excellent talks. Many thanks. Are there any questions? Please, Maurizio. Maurizio Prato.
Thank you very much for your talk. You have shown MOFs for water, for CO2. So do you ever get competition between different guests, or the functionalization plays a role of excluding any other possible guests?
I think one of the most powerful aspects of this chemistry is that not only can you design, let's call it the skeleton, in the case of MOF, the metal organic skeleton, with precision, but also you could go in, because the bonds are strong and the material is chemically stable, you could go in and functionalize the organic. That's really the power of this chemistry. Functionalize the organic so that you can fashion the interior for a very specific trapping of a molecule from among mixtures. Now, if your design is not so good, yes, you will not get selectivity. But if your design is good, like for the CO2 capture, we put amines, and these amines are modules that specifically take up CO2. And sure, it takes up water, but the water is helping the equilibrium be shifted towards the CO2-bound products. Not too much water, just enough to push the equilibrium to. So in the case of water harvesting, only water goes in, because water binds stronger than anything else in the air, like CO2, argon, nitrogen. Even if they go into the pore, they will be expelled. Now, if you have octane in a gas station, well, that's never going to get into the pore because it's too large. So there's shape and size selectivity as a result of the pore size, but also there is chemical selectivity. Is that certain molecules that can get in could be distinguish based on their electronic structure or their chemical behavior. Yeah, thank you.
Giulio Tonello.
This is wonderful. I was thinking about the possibility of using isotopically altered material for a fine-tuning of the efficiency. Imagine isotopically altered water or CO2.
So, very good idea. There's several groups actually doing that with great success. That's a very good idea. It's already being, I think there are even some publications already out there on this topic, yeah, using MOFs. Thank you.
I have a question, if you don't mind. When you have shown the football camp, it reminds me the zeolites, where in a cubic centimeter you have hundreds of square meters that you can collect into it. And the second question is about, we emit about 40 gigatons per year of CO2 in the atmosphere. You said with 100,000 tons of MOFs, we could capture 0.5
A year.
A year.
Yes.
Do you want to comment? Because we would need 8 million tons of MOFs per year to
Well,
capture.
we are producing 200 million tons of sulfuric acid every year.
Yes.
Imagine if our most powerful economic countries, G20, say, you know what, we need to make 8 million tons of MOF, of this cough. You think they can do it? Of course. The human will is unbelievable. When we set out to solve a problem, we always solve it. I don't think there has been one incident in the history of humanity where when we set out to solve a problem, we couldn't. That is really a true statement if you look throughout the history of humanity. So I think 8 million tons is trivial to the world chemical industry to produce. I'm not saying that it's something that we don't need to work through. We will. I mean, nothing is easy, but it's the difficult problem of capturing. For each CO2 molecule in the air, you're trying to pluck it out of 2,500 other molecules. That incredibly difficult problem has been solved. The rest is just a human will. Like I said, if it's not a crisis, it won't be solved. We need to make it a crisis. We need to talk about it as a crisis. I'm sorry, I didn't understand your first
The
question.
zeolites.
What about them?
The minerals, the zeolites.
I know, what about them? What was your question?
Because they have the capacity to absorb a great amount of gas or water or whatever.
In almost all cases, zeolites, for example, in the case of water harvesting, sure, they take up water from very dry air, but you need to heat them up to 200 or 300 degrees C to remove the water. So for water harvesting, they're not viable. For CO2, they're not as selective. Especially, they cannot take up CO2 from air. So very early on, I realized that zeolites are good at what they do, and they're good at what society cares about around the time that they were invented, which is oil-based, petroleum-based stuff. Well, now we have a new kind of materials, and they do things that zeolites can't do. And that's the best direction to go. Don't try to compete with zeolites. Nobody can compete with zeolites. I think that they're wonderful, but they are materials of a previous era.
So you are saying that on the basis of the structure of the molecules that you want to absorb, you can theoretically predict the structure of a crystal? There is a theory, is a good theory, or you just
with
try?
slight modification, we can predict. If you give me a molecule, with some work, I can work backwards and craft the interior of the MOF to absorb that molecule, and then use computation from the very beginning to optimize and improve the quality. But we still cannot predict fully the actual crystal structure, space group, and so on and so forth. But we can predict how.
It's not a real theory, a real theoretical background. Just try.
No, it's a real theory. I mean, Laura, you can answer that. I think there is a real theory behind going from what you want into crafting computationally that pocket and looking at how strongly, let's say, a molecule is going to bind into that cavity. That's real theory and computation already developed for that, and it's doing it very, very well. Pardon? Quantum mechanics, yes.
Thank you so much. Two more questions. Yes?
Thank you for this very interesting talk. I'm wondering if in the 10-minute cycle, I suppose you have also to make a thermal cycle, so you consume energy. Are the cough better than the MOF? They have both advantages, stability and also on the energy they consumes to be operated?
What is really interesting here for CO2 capture is that you can modulate how strongly the carbon dioxide binds to the framework. And so you only have to heat up, I think, that cough to 60 degrees Celsius if you want just the right kinetics of taking up and releasing in 10 minutes. That's 60 degrees Celsius. Well, that's waste heat. So you don't need to apply new energy. Just take the waste heat in industry that is being wasted right now and apply it to remove the CO2. And that's the bulk of the energy that is needed for carbon capture. So I think that's where coughs are useful for the extracting CO2 from air. Now there are MOFs that are robust enough to be deployed like the one that I referred to for the cement plants, because cement plants have 35% of their flue gas, 35% CO2. So MOFs work out very well there. But MOFs, to my knowledge, no MOF at least has this high performance that the cough has for CO2 capture from air, making coughs the ideal choice for solving the carbon problem in the air.
Thank you, Professor Yagi, for the bright presentation and also for these MOS that are a future bringer. You might remember we met last year when you got the Balzan Prize. Paola Antolini, I am a journalist, I am as well anthropologist. So as you know, United Nations in the General Assembly, August 2023, decided to declare this decade as a decade of science for peace and sustainable development. You have a beautiful, also personal, successful story, being, if I can resume, originally a refugee from Palestine, the first Nobel laureate from Jordan, and we are very proud of you. So what do you think? Can we imagine that you will attend, for example, the COP30, or that we can imagine to be stronger together for science, for peace, and sustainable development? For this magnificent MOS. Thank you for your personal vision of
Thank you.
science for society and the immediate future. We need you. Thank you.
Thank you. Yeah. Thank you very much for those warm remarks. I think science is maybe the only language, or one of the very, very few languages that you can talk across borders. Even adversaries meet at meetings and talk. Even people that are thought of as enemies, they can talk chemistry, they can talk science. A chemical formula in Italy is interpreted and read exactly the same way in Japan and in the Middle East and in the US and China. So it's a beautiful common language. I think that for the future, we need to be stubborn about making sure that science continues to focus on facts and not to be drawn into the hullabaloo going on in the social media or on elsewhere. There's a mountain of garbage out there, and I know that the facts have to work themselves through all that garbage. But the facts are very important, and science produces facts. So I think we need to continue to think in that way. And facts is what we need for people to get along. And so I think that science is a very promising approach to talking across borders. In my group, I mentor Palestinians the same way I mentor a Jordanian, a Chinese, and Israeli, with no a woman or a man, regardless of their gender or whatever. All this is part of the scientific innovation. And why? Because we put science language above everything. Okay, and so I think we need to continue to do that. We need to encourage education, and I hope all of us who come from research-strong countries will just spend 5% of our time dedicated to helping researchers in the non-research-strong countries. Find ways of, whether it's a global seminar that you hold that people from other countries can plug in, or actually visiting other countries and talking to young scholars there and helping them out. I think that that's what we can do as individuals. We can take just 5% of our time to do that.
Last question.
From an outsider, thank you for a beautiful talk. And about your impassioned plea, do you think that politicians will hear it?
My invention.
Your impassioned plea for doing something concrete. You're very convincing, but will you be able to convince politicians like in your country?
Well, I rather spend the time in the lab than try to convince politicians. I think society as a whole has instruments with which they can select politicians that base their decisions on science. And the science says that we have a climate problem, a crisis actually, and so it's a societal problem. So I rather do the science and I put it in the lap of society and let society decide what they want to do with it. I only have 24 hours a day and I rather spend them on science. Thank you.
Thank you so much.